Hi everyone. Thank you for coming to my talk, and I hope you're having a great conference. Uh, so the topic of my talk is journey of developing a performance optimization feature. Last night while discussing with a few people at the dinner, I realized that this is not a very great title because everyone had a different idea of what this talk might be about. So maybe I'll start with giving a little bit of like a few lines about what this talk does not contain. So, and feel free to then make a call for yourself if you would like to continue sitting, or feel free to hop on to the next another one. So, excuse me. What this talk does not contain is, it does not give you information about how to optimize your database in general from a DBA's point of view. It does not give you information about a feature which is highly optimized. So these are the main two things which I think I heard that people thought this talk might contain. What this tells you is a journey of going behind the scenes in Postgres and developing a feature which can result in performance improvements. So this is kind of, there is no guarantee that there will be performance improvement at the end of this talk, that you'll go back and thinking that, oh, this is this cool new feature which gave us such a good performance improvement. But this is just like an exploration of how one can develop a feature or go about developing a feature in Postgres that can help you, that can help improve Postgres performance. The specific topic that I'm covering is physical replication. So with that, let's get started. Okay, now just let us look at some basics. What is physical replication? It is a block by block or byte by byte transfer of your WAL files from master to standby. Just before this talk, there was a great elaborate talk on what logical replication is, and so that covers that aspect of replication. But what physical replication does and how it is different from logical is that it transfers your entire database, not just one table or particular rows of a table or particular columns of a table. It copies the database verbatim from one server to the other. What are the types of replications? Synchronous and asynchronous are two types of replications depending on the consistency level you need, and it is set by a GUC. The GUC is synchronous, is called synchronous commit. Can be set in PostgreSQL.conf file, as some of you may already know. There are various settings to this GUC. One is off, which means it's asynchronous replication. That means it does not depend on whether the change is actually sent to the standby or not. It just commits its own transaction locally without waiting for any guarantees. It does not even wait for the transaction to be flushed locally on master. So there can be a little bit of delay between sending a response to the user that, okay, this transaction has been committed, and when actually the transaction becomes durable. This can be done for performance reasons if there can be some leeway between the commit of a transaction and the durability. Second setting is local, which means that the transaction is considered as committed, and user has been sent a reply that the transaction is committed only after the transaction has been flushed to disk. This is the general mode where which guarantees durability of a transaction, but this also does not care whether the transaction has been sent to the standby or not. The second mode is remote write, which basically commits a transaction on primary only if a transaction has been written to a file, to a wall file on standby. This does not mean it has been flushed, but just written to a wall file. There is remote flush. Remote flush is something which, as you might guess, that transaction is considered as committed on primary after the transaction has been flushed on standby. This is also named as on in the GUC file. So if you set it to on, it will actually work as remote flush. Remote applies the last stage where all the guarantees are met. Basically, you want your changes to not only be flushed to disk, but also applied to the standby. So whatever you're reading on primary, you can read on standby as well. So that's what these synchronous commit modes mean. Just let us look at overall flow of physical replication. So as you see on the slide, there is a primary on which the data changes are made, which results in wall to get inserted. It is written to disk. It is then synced to disk, and then wall sender reads these wall changes from disk, which are written in a wall segment, and it sends it to standby. What happens at the standby? Standby has a wall receiver running, and it receives these wall records, which are essentially libpq copy messages. That's how streaming replication is implemented underneath. And these messages are received and directly applied to the wall files. There are no buffers on wall receivers, so they are directly applied to wall files. And then they are synced, and once they are synced to the wall files, then only a startup process, another process on the standby, can read this from the disk and apply it to your database. So as you can see, there is a lot of disk write happening over here. From the time the data is sent from the primary to the time that the data is available on standby to read, there are a lot of round trips from to disk, both on primary as well as on the standby. So yeah, I mean, that flow, I hope, gave you like a overall picture of how the wall is being transferred. There is another component to this, which is wall buffers. These work on the primary. So what happens is that when all the backends write to your database, where all those changes go, so all those changes are recorded in the form of wall, and those are first inserted to wall buffers. Then after the wall buffers become full, they are getting written to the disks. So these wall buffers actually are something that can be set by a GUC, and these are typically set to about 3% of your shared buffers. Setting this value high is important to if you have a lot of concurrent workload, because all the backends that your Postgres database is running is actually, all of them are actually writing wall to the same wall buffers. So it is important, if you have a lot of concurrent workload, that you have the same, you have a higher setting for this GUC. However, wall in the wall buffer is flushed periodically, which you'll see in the next slides as well. And one point at which they are flushed to disk is when a transaction is actually commits. So for a synchronous transaction to be committed, a wall has to be flushed to disk. So at those points, the wall is flushed to disk, and that's why setting it to a very high value also will not give you a lot of performance gain, because naturally the wall has been flushed to disk, and now that wall buffer can be reused for other writes. So you are not constrained by memory over there. So this was a bit of like introduction of wall buffers. I'm just trying to give you introduction of some basics because I think this will lead to the optimization I'm planning to talk about. So now let's look at what walls fsync is and when it happens. So as I already mentioned, wall fsync is when the wall is flushed to disk and when it is made permanent and durable. So this happens when for a synchronous commit, it happens when a commit happens on a primary. It calls xlog flush. There is another process called wall writer, which is also responsible for making these wall records durable. But wall writer works in the background. It does not work in the foreground when you're running the transactions. It does not hamper the progress of transaction that way. It runs in the background and it periodically tries to flush wall. As in when your wall buffer starts to grow, it tries to keep it in check because then otherwise if it becomes full, then it will start blocking your active transactions because they won't have any place to write wall. And they will have to first evict the walls before they can actually proceed. So generally wall writer works on writing wall files to, wall records to files, and periodically it also flushes them. That depends on certain GUC parameters like wall writer delay and and there's another one which tracks the number of the bytes of the wall that you've written. And if it is higher than that value, then it will start flushing it to disk. So this is where the wall sync comes in. Now let us look at identifying the bottleneck. So for that, let us briefly look at how wall sender works underneath. Wall sender is a background process in Postgres, as you may know. It runs an infinite loop. And these are the operations that are run in that background worker. As you start, there are some housekeeping operations that happen. Resetting a latch is used to wait on a particular condition later on, mostly used by a lot of like long-running, infinitely running background processes in Postgres. Then there is check for interrupts. Since it's a long-running process, it needs to be interrupted. So there's that. Then there are other like processing of standby replies and other functionality that runs, followed by there is an exit condition check in that loop, which checks if the standby is done receiving wall, so standby wants to stop, and the output buffer is empty. Output buffer is something that is written, that is sent to the network from the wall sender. So if it is empty, then okay, and copy done has been received, then the wall sender exits. It's like a clean shutdown. And if there is, okay, the exit condition is not met, then it goes on to check if the output buffer is empty. If it is empty, then it means that it can read in some more wall files in its output buffer to send it to the standby. So now it's reading in some more wall into the output buffer, and that read happens from the wall files. There is also a case where this wall can be read from the buffers as well if they are not flushed to disk. So first the wall sender, the read wall into output buffer logic first checks if the wall is available, is not already flushed to disk. It reads from there, otherwise it reads from the wall files. And in most cases, like in more common cases for large transactions especially, it happens that the wall sender has to go to disk because the transaction takes a long time to commit, and by that time the wall buffer eviction logic has stepped in. So, so that is one part of wall sender logic that results in a lot of read from disk. Then okay, then if output buffer is not empty, it goes on to try to flush that output buffer over the network. So once that completes, it goes on to see if the wall has been caught up, if it has, which is the last a diamond shape that you see. That happens if the wall has caught up, or if the output buffer is full. That means there is lot of wall in the output buffer to be sent over the network. So wall sender takes that time to sleep, because if it goes on checking and trying to send wall periodically, like very frequently, while the network is congested and while the wall records are sent across the network, then it will cause the burn of CPU cycles. So that is when the wall sender sleeps, if it sees that the output buffer is yet to be sent over the network. So these are the main steps that happens inside the wall sender, and if we analyze them, there are possibilities of optimizations that we'll see in the future slides. Like we already discussed, the wall sender can only send wall that has been flushed to disk. It cannot send wall that has not been flushed to disk. This is for a simple reason that we cannot have standbys get ahead of masters, because at the standby we don't buffer anything, we just completely go ahead and write to wall files. So we need some check or gate mechanism or something where we guard the wall files being sent to the standby, because we don't want them to be written and persisted if they have not been persisted on master. So that is one of the sort of shortcomings, in the sense that it can hamper long running transactions. So if your transactions are long running, what happens is that they accumulate in wall, because the flush has not happened yet, commit has not happened yet. So if commit has not happened, the flush of wall files will also not happen. There is and while you are going on inserting into the wall records and generating more and more wall, you cannot send them to over the network, because the flush has not happened, and this results in the network being underutilized, in the sense that when there's a long running transaction, the data is not being sent, but when the transaction commits, you'll send in bursts, like the amount of data sent after the commit will be high. So there'll be inefficient utilization of the network here. It can also increase in the disk IO, because since a large transaction can occupy space in buffers for a long time, chances of it being written out are higher, and thus means that the wall sender is ready to when wall sender is ready to send it, it will have to go to the disk to read it. So I'll just give you a big, like a short intro on perf profiling, because we're going to see the output in the next slide. I've used perf profiling here to measure the CPU cycle consumption. It samples the execution of various instructions on the CPU at a fixed interval, so that when it is aggregated, you know where the CPU was spent most. So it also contains a call graph structure which records the full call stack. So the commands I used are perf record, which records these samples and creates a perf.data file. Then I've used a tool called flame graph to visualize these call stacks to make it easier for anyone to actually debug it. Yeah. So that was a short intro of perf. Now if you look at this, this is, sorry about the unknowns there, because I think this was run on a cluster which was optimized to a level that these function calls got, the debug info for these function calls was not available. So, but what I want to show on this chart is, if you can see, You can't see the percentages here, but I have noted down the percentage of time spent for sending the wall is about 18.5% of CPU time, and receiving likewise is also 21.79%. So to give you a little bit of a background, this was run, this actually profiles the wall sender, and this the cluster that is running is set up between two Azure VMs, which one is in India, other is in US, so high network latency. And we have set up a physical replication with synchronous commit is equal to remote write on it. So, so it waits, so the commit waits for the round trip between the master and the standby to confirm the commit. So the TPS is impacted by the amount of time the wall is taking over the network. So here what happens is we can see the significant amount of time is spent over the network, or rather waiting for the wall to get sent to the standby. Here in this particular case, we don't see a lot of overhead from reading from the disk, because it was a 40 KB transaction that I ran. So this, I ran a pgbench with 40 KB transaction. I'll give you details of the benchmark also in the next slides, but the transaction being run by a single backend was about 40 KB, and the wall buffers was 8 MB. So the walls didn't get evicted so fast. So wall sender could find those in the wall buffers. So that's what explains that there is there isn't a lot of read, but there's a lot of network activity happening here. So this is also same scenario, profiling the wall sender, but with a much larger transaction, actually an extreme case where the transaction is of the size of the wall buffer. So wall buffer is 8 MB, transaction is also 8 MB. So a lot of time being sent, 43.5% of the time is being spent sending, and about, like you can see, 17% is of the time is spent reading from the disk. So this again happens because of the long running transaction as explained, and the wall has been written out to disk. So whenever wall sender is ready to send it, it has to read more from the disk. So in such scenarios, I think there can be some improvements that can be made to the wall sender to mitigate this. The core idea here is that we send unflushed wall also from primary to standby, and we don't wait for a large transaction to finish committing and flushing before we actually send the data. There is a caveat here that we cannot send too small packets also, because it can result in an overall increase in the system calls, network system calls, and also the overall size of the data, so that because each of the packet is prefixed with a header. So there has to be a balance between sending just one byte or sending only after the transaction has committed. So currently in my implementation, I chose that size to be 8 KB, which is the block size in standard block size in Postgres. So so as soon as 8 KB of wall is written in the wall buffers, we don't wait for the wall to get flushed, but we just start sending it to the standby. So the wall replication protocol has been modified to include flush pointer as well, because there are a lot of metadata we send along with the wall in the replication protocol. One additional field that we've added is the flush pointer. Standby uses this flush pointer to determine whether it is safe to write wall to disk, because as I mentioned, we can't write unless it is flushed on primary. And wall receiver buffers this unflushed data until it is flushed on primary. So we'll discuss more about the wall receiver side of implementation ahead, but this is more like giving you an overview of the idea that is implemented here. So just a bit of like finer details of wall sender changes. So wall sender uses like a 3-tier read strategy, which is, as I mentioned before, currently, there is a mechanism to read from buffers before it can read from disk, the wall sender. That has been extended a little bit to read from buffer, basically the entire sort of segment or the range of wall buffers, sorry, wall records to send has been divided into the wall records which have been flushed and wall records which have not been flushed to disk. So the wall records that have been flushed function like how they function now, that the read happens from the buffer and then from the disk. But for the wall records that have not been flushed, the read happens from buffers only, and so because they are not on the disk yet. So yeah, I think that is the detailing over there. And then for this to happen, we need the wall sender to be woken up as soon as a sufficient wall has been written. So that pointer has also changed. So it used to get woken up at flush record pointer. Now it gets woken up and it records the insert record pointer. And it also sends the flush position like we already discussed. So what we observe with this is like it actually benchmarking this wasn't easy because the performance improvements doesn't show in the TPS for most of the cases. I had to like set the wall sender size and the transaction size and the concurrency to a level which is overwhelming the wall buffers enough, and also the network to be a constraint between the primary and the standby to see actual real TPS gains. More on that later. So, when the gains are seen, mostly those are because the replication latency has been reduced because the wall reaches the standby before it has been flushed on primary. As a result of this, the flush on the primary and the standby happens almost simultaneously. These are some details about the benchmark. The configure flags used are this. So I've used O2 because that optimizes the code and it's suitable for benchmarking. Essentially try to have enough concurrent clients so that the wall buffers are overwhelmed and a lot of wall buffers get fully utilized, so that the wall sender has to go on disk to be able to send. Used pgbench -j to set the worker threads equal to the CPU core count. Also there is this custom workload that I've used with pgbench command to run the large transactions. Wall IO is measured using pgstat IO, which is a monitoring feature in Postgres, or a monitoring function in Postgres, which can give you the IO the disk IO for all the backends of the Postgres. So I've measured it specifically for wall sender. This is what the script looks like, and the main takeaway here is that clearing the drop caches every time for each run. The output is aggregated over multiple runs, I think 3 runs, and a custom custom SQL is executed with pgbench to get the optimal wall generation. So with this, I see if I apply the wall sender changes of sending wall before flush on standby, without the patch TPS was 125, with patch 133, about 5% increase, not very not a lot, but some increase. Wall read IO has also reduced with the patch. Without the patch, it was higher. So now, yeah, so this gives you, after applying the patch, how the wall sender profile looks like. And what you see is that I think there is definitely less time being spent sending the wall because the network bandwidth has been utilized more effectively. You do see that now there is this xlog send physical function that has come up, which wasn't there, and which reads from buffers. So because we are reading more more frequently, we are sending smaller chunks of wall. This has shown up now, but overall I think there's net improvement because sending over the network is more expensive in this case. So now let's look at wall receiver side of the story, because this is where the seeing the real gains become difficult with this particular feature, and which I'm facing right now, because we do need to change wall receiver to be able to handle the wall that has actually come before flushing, right? We can't do business as usual here, and those changes result in actually impacting the performance negatively. So just would like to give like a quick run through of what happens in the wall receiver. So this is again a flow of wall from primary to standby, and you can see that the wall has been transferred to the receiver process, and once the receiver receives it, it goes ahead and writes to the segment file, which is xlog receive write function, following which it flushes if and makes it durable. So at each point we record certain pointers which are recorded in the shared memory, so that the progress update can be sent to the primary. So when a wall has been written to segment files, we record a write pointer and send it to the primary, and so on and so forth. And there are functions executed to send responses to the primary. Once the record has been flushed to disk, a startup process reads these records from the disk and goes ahead and applies. So the challenge, challenge now with sending the wall before flush is that the frequency of writes to this disk file has increased, because earlier the receiver process used to write in bigger batches. Now the receiver process is writing in smaller batches. It directly writes to disk also. So and for correctness reasons, we can't let it do that. So there are certain implementation options here at this point, which we will look into. So one option is to let the unflushed wall live in the buffers on standby. As I mentioned, currently there exists no buffers in the on the standby. Wall receiver doesn't use any wall buffers. There is infrastructure that exists on the standby side for wall buffers to be used, but we don't define wall buffers. But with these changes now, one solution is to have these wall buffers and prevent the standby from writing unconfirmed data to disk. So this is one aspect of the solution. The other solution, similar, we had wall buffers here, but we also were doing that. We were doing the writing to the wall buffers in the receiver only. But now, what we can also do is we can try to offload the writing of the buffers to a separate process, so that since we are adding this additional step in the wall receiver, because earlier there weren't any wall buffers. So the wall if you think of a remote write path, before a standby can confirm that the wall has been written to disk, it has to do one additional step of writing to buffers, reading from buffers, and then writing to the file before confirming to the standby that the wall has been written. So to eliminate this extra step, or rather eliminate the impact of this extra step, there is a possibility to also use a wall writer to do the actual, like how it exists on the primary, to do the actual writes and the syncs asynchronously, and have the wall receiver only write to the buffers, and startup process also read from the buffers, because currently that also doesn't happen. So there is some benefit of using buffers here, which is transferred to all the other processes as well if we use a separate writer process and a full-fledged wall buffer. So this was an alternative implementation. All of this is under testing right now. I'm still working on doing the profiling for this particular side of the implementation, so that the improvement that I saw on the wall center side is not negated by these changes. And just wanted to put it out there just to describe what are the different solutions that can be implemented on the receiver side. Also, there's another problem that both of these approaches contain, which is if we have wall buffers on the wall receiver, and if the wall buffers are not big enough to hold the unflushed wall from the primary, we will have to think of solutions, because we can't just go ahead and write those to files. So, there are some options of solutions there as well, which need to be profiled again, which need to be benchmarked. So that's part of to do. This was basically when the wall buffer becomes full and the standby has yet not flushed the wall, then we need somewhere for these wall records to go. So they can go to a file, a spill file, because we can't write them directly to wall segments. We have to write only after flush, so we write them to a spill file, but this will introduce additional overhead of writing to disk again. But if these are like rare occurrences, because we don't expect the wall to accumulate so much, or the flush record, the flush to happen so late on the primary that the wall buffers get full, because there is a logic to evict buffers on primary, which is driven by the wall writer. So if we have like size of the buffers on the receiver 2x or 3x of the size of the buffers on the primary, the chances of wall buffers overflowing before the flush has happened on the primary are too low. But when it happens, we need a way to handle them. So one can be the spill file. The second solution here is to send a pause like notification back to the sender, asking the sender to just hold on and not send more wall until it flushes some wall. Other third suggestion, which I actually got on hackers mailing list when I posted this WIP patch, was have this flush pointer written in the wall record itself. So we want this information to correctly apply wall on the standby, and this information can be stored in with the wall record itself. So whenever wall file is read to be applied, this wall record is also read, and then we can confirm whether the wall we are trying to apply has LSN greater than or less than this flush pointer LSN, and then accordingly take the call to apply or not. So this one, yeah, I mean this one I think won't require wall buffers even. The wall records can be directly stored in files, just that while applying them, we have to be careful which ones to apply and which ones to not. I think this was in summary all about the optimization feature that I wanted to discuss. Like I said, this is still a WIP feature and has been proposed as a WIP patch on hackers list, and I am open to any collaboration that anyone would be interested. If anyone is interested in helping me finish this performance testing and actually get a feature out, I'll be really glad. Shout out to Andres Fron from Microsoft. This is based on his idea of improving physical replication. And also Melly, who has worked on who was part of Microsoft PG OSS team and has worked on initial implementation for this. That's it. Thank you. Thank you for listening. And I do have a couple of slides. Please. This is POSET conference that is sponsored by Microsoft. It's a virtual conference, happens every year, and it's a very well attended one. So please do check out. If you were taking pictures, I'll hold on. And yeah, feel free to give review of our work at Microsoft booth. And talking Postgres, Claire is here. This is a fantastic podcast. Do check out.